Hi everybody, this is Bob Cheeseborough again. This is our walkthrough of a bone hunt, discovering dinosaurs with AI. So today we've got a special issue. We're going to go through the code walkthrough and the slides that we've used in the workshops to allow you to follow us along in real code and create your own dinosaur bone hunting map. So with that, we're going to go ahead and get started. I want to share with you, before we really get going here, just a little bit about why I get so passionate. Why am I so passionate about these dinosaur bone hunting activities? And, you know, why am I so excited about AI and these kind of things? And I wanted to start with just the excitement around the bone hunting itself. Because, you know, really for us, for me and my family, this is it's the thrill of discovery. You know, we're finding things that nobody has discovered before, and we're reporting it into the scientific record. So, and we're making memories. So with that, let me go ahead and introduce you to some of the adventures that informed and helped us to stimulate the thought process around, hey, can we do this with AI? So here's just a couple of minutes of bone hunting adventures.
Let the adventure begin. Oh, this is amazing. Can you record? Yeah, I'm recording. So this is all bone. I don't know.
Show me again.
So this huge bone, look at this. This comes all the way over to down to here.
Yeah.
This one, which I hadn't seen initially.
Yeah. Okay.
This one is the one that pokes through on the other side really big.
Yeah.
This one's the one that pokes through on the side really small.
Yeah. Yeah. Yeah.
This is a whole big amount of flowy, circly bone. I was like, well,
I can't believe that, Ben. Here, high five again. That was awesome.
That was amazing.
We were poking around down here. Look at this, guys.
Oh man, so there's fragments. This is in situ and this is not. And this is all connected.
Yeah, it's all connected.
This is all, I didn't realize that. Oh man.
Hey, Dad.
Bone.
But he said it louder than that. We're trying to beat the storm. Look at that. Wow, let's ride that one. Good job. Good job. We walked right past it. Wow. Wow, that's a big one.
Look at the socket. This is a socket. This is amazing. I couldn't even say anything when I turned around. I was just like, exactly. That's the shape. Look at this. This is solid bone.
You can see the serrations. It's just like,
yeah, I think this has got it. This is probably part of the Diplodocus, I bet.
Float.
Three pieces.
Yeah.
That is awesome. That's a definitive tooth, though, I think.
Yeah.
Nice.
Yeah, that's awesome. Awesome.
That
awesome.
is so
awesome.
exciting.
Yeah.
What is that?
Nice.
That's got
So,
to be
so I
a
don't.
scapular or rib or something.
Yes.
Top of a rib. That's in such clean condition.
Isn't that great? Yeah.
That's directly in the salt wash, no question about it.
Yeah, exactly.
So
Yeah.
clean.
Wow. All right, guys. I think I have a tooth here.
Really?
Come take a look and see what you think. It's a tiny little thing, but I think it may be a tooth. No, there's bone all right in here. Look at this thing.
Oh, I think you're right. That's a tooth. So right.
That's a tooth.
Yeah.
Dad.
Yeah. All right. Well, then these two things must be bone, and it must be coming out of this limb bone right here.
Nice.
Bone, and look at this. Look.
Nice. Oh, nice.
Okay, we're just having lunch.
This has been really a great day.
So that's why we're so excited about the dinosaur bone hunting. Now, you're going to follow me, and you'll be able to get into a sandbox that we call the Intel Dev Cloud. So you'll be able to do this code. You just enroll. It takes a few minutes. You can log in. You'll be playing with these Jupyter notebooks just as I'm doing in this code walkthrough I'm going to show you. The code is actually found down here in the GitHub link down below at intelsoftware/Jurassic. So you can play the game at home. And so what we're going to do now, I just wanted, by way of continuity, remind you of some of the things we covered in this series. We'll go over it rather quickly here because we have those other videos in the series. But how do you know if it's dinosaur bone? Let's say that you go out in the desert and you pick up a fossil. You're pretty sure it's a fossil. How do you know it's bone? Well, one thing we look for are these osteon patterns. And so this is these little concentric cellular formations within the rock. That was the way they formed the way bone forms. And then when it fossilizes, in many cases, it does this. And so there's spongy bone and there's compact bone. And that's referred to in one of the episodes in this series. But I just, by way of reminder, wanted to show you that you just don't look only at the shape of a bone and say, oh, that looks like a bone to me. There are other evidences that you use to confirm that maybe it's the shape, maybe it's the context of this long grain structure, these cell structures, these osteon patterns. And so how do you know if it's bone? Also can be informed by the shapes. So here's where the shapes of the bones can tell you a little bit more. So, we've got a femur on the right side over there, embedded in sandstone. We've got a tooth in the lower middle. We've got a part of an ischium of a Allosaurus hip in the upper middle. We have another Allosaurus hip in a different location in the upper left, on the left side there, upper left. And then we have an Allosaurus claw down there with the tape measure on the lower left. And so combining the shape information with that other macro sort of view of the bones will confirm that it's bone. And in these cases, it helps us to identify the species. For example, the tooth in the lower middle there is a Camarasaurus tooth. That was a long-necked dinosaur from the end of the Jurassic. And that Allosaurus claw told us then that all the bones that we were finding around there were Allosaurus. And so it helped us to identify what it was through context. And so this is just some of the stuff that you need to kind of bear in mind, so that we're not just randomly throwing waypoints or dots on a map and trying to predict dinosaurs. There's a method to the madness. And part of that method to the madness is the depositional environment. When these rivers in the ancient time formed, the dinosaurs would congregate there, and they lived and died along and near those rivers, and sometimes floods or whatever happened, and they would be swept down and encased in sandstone or mudstone, and they would be eventually fossilized. And the marshy areas that were formed from volcanic fallout, volcanic ash that fell in these watery areas and lakes and ponds, would form these clay stones, as I understand it. That's that kind of elephant hide looking soil. And then the river channels would deposit sandstones. And so that's what those big blocky boulders are. And the dinosaurs could either be trapped in the rivers and be caught and died and fossilized, or they could be caught in those marshy areas. And so we find bones in both. But you'll notice the textures there are not your average variety desert scenery. There's a certain pattern in terms of the colors and the textures, and that's indicative of the Morris and brushy basin formation. And so we're going to train the AI to look for that. What the brushy basin looks like from the air, from an aerial photo, a few thousand feet up, is something like this. So you see the Neapolitan ice cream sort of look. This looks like a birthday party gone awry, right? With the ice cream melting, Neapolitan ice cream melting, and maybe some cake up here. And that's what the AI is trained to look for, are these blocky, bouldery, and change of color patterns. That's what the AI is trained to look for. And that's what we look for when we look at an aerial photo or we look at Google Earth. We use this to inform our hunts. And so right here you see a likely spot, and in fact we found bone there, and the same thing with this. And so these patterns are what we're training the AI to look for. Now, those patterns don't just happen everywhere. They happen in certain locations in the world. In Portugal, for example, they have something similar to the Morrison Formation. Here in the United States, in the Western United States, we have what's called the Morrison Formation. And I've highlighted in red roughly where the Morrison Formation is found. And primarily it's in Utah, Colorado, New Mexico, a little bit of Arizona, Wyoming, a little bit into Montana, and some of the Dakotas. So, but those red dots are where you'd want to go, but that's still a vast area to search. Now, if you were to just do a random walk through Texas up through Washington, and you just randomly walked your way around, your likelihood of finding dinosaur bones is very, very low, okay? Very low. So you have to improve your chances. And so one of the things you would do is you would go hunting in these more red areas that I've colored on the map. These represent the Morrison. But there's still an awful lot of walking. That would be tens of thousands or more of miles of hikes, or who knows how long, to try to traverse. And you would begin to find bone randomly but it's not a perfect way to hunt. And that's the way we started, was just random walks through these kinds of things. But as you use an AI, then you can inform where within those red dots are the smart places to go, as I've just described. So the thing that you do first is you create to create a dinosaur site treasure map, a heat map, if you will. You collect the data, the waypoints of where you find bones. And by extension, you keep track of your trackway that you use, your tracks, so you can identify the areas where you also did not find bone. And then you can cluster and classify. So you can use clustering, and we'll show you how to do that today, to identify the birds of a feather. So find the areas. If you found some bones, like some of the Allosaurus claw, and you find other bones very nearby, well, then those bones that cluster near that Allosaurus claw have a much higher likelihood of being belonging to an Allosaurus. And the same thing with the Camarasaurus tooth. If you begin to cluster the bones that we found near the Camarasaurus tooth, then you'll have a higher probability that those bones and the femurs, the things we're finding, were probably Camarasaurus. And so clustering can help. And sometimes we just do that in our mind's eye as we're out there in the field. And sometimes it's trickier than that. And we want to do it actually programmatically and help us to delineate where different bones and teeth and things like that are found. And so the second thing that we do is in this exercise, we talk about semi-supervised labeling of the tabular data. And I'll talk about that a little bit more as I get into the workshop. But it's one thing to say that we found bone in a certain location and I've got waypoints. And then the rest of the world that I've ever stepped foot on, I'm going to say, well, there's no bones there. Well, that's not a very good way to go about it, because just because I found a bone right here at this local certain location, if I walk 100 yards away and I don't find a bone there, the likelihood of finding bone there is still pretty high. If I find 2, 3, 4, 5, 10 bones in a certain location, and then I go 30 or 50 yards away, my likelihood of finding bone at that new location, even if I don't see it with my eyes, is still very high. It may be an observational bias. Maybe I just didn't see it. And so you need a way of defining that just because I didn't find a bone there doesn't mean it's a non-bone location. And so you have to have this intermediate case. And so we'll go into that a little bit. We'll just talk about it briefly. And then how we collect the aerial photos. Now, in this exercise, we collected bone location data for bones that we found in New Mexico. And I've collected aerial photos from those areas. And then we trained the model on aerial photos, not on the actual bone locations, but the aerial photo spanning that large region. And then said this large region is a bone holder. And then other images, obviously, for non-bone holders. And so once we do that, we label those photos we just put the folders, the photos into a folder, and that's how we label them. And these folders have a structure, and we'll go into that here a little bit more when we get into the code. And then we train a model. Now we use the ResNet model, ResNet 18 to start with, and we train that model. After we train the model, we optimize it. And this is where we use OpenVINO to come in and optimize it. So whether we run it on a laptop that has a GPU, an Intel GPU in it, maybe an ARC GPU, or some of the new GPUs that are coming out in Intel's lineup on servers, then they could be run against that, or otherwise we run them on the CPUs. And so OpenVINO lets us target that in a very easy envelope, an easy way to do that. And then what we do is we take a brand new location, not from New Mexico, but from Utah, and we go out and say, well, let's predict where bones would be. Now, we actually have hunted bones out in Utah as well, so we have some holdout sets that we know the ground truth, but we let the map predict what it's going to predict, and then we can do some scoring and see how well it worked. And then we created a dinosaur bone map, and sure enough, we found some bones that indicated a map that said, hey, that little building that happens to be at Dinosaur National Monument, the one that we happen to know holds several hundred bones, and a lot of those have been collected by the Carnegie Museum back east over the last century. It predicted, hey, that's a good spot to go look for bones. And so there's method to the madness, and it's not perfect. But we did find bones in Utah, confirming our model, and even though it was trained on New Mexico. So it's the ultimate of having a different holdout set or a different, what we're predicting is kind of wild. It's not stuff that we trained on explicitly. So just to describe a little bit about what we're doing in this AI series of notebooks. I've got about 12 notebooks, maybe a few more than that, parallel little branches that you can take, but the primary flow is about 12 notebooks. And it basically covers a wide swath of the AI lifecycle, everywhere from data collection through the data processing analysis, the model training, the model testing and evaluation, optimizing the model, which a lot of people forget about, so that you can deploy it at scale and massively. And so then you do the deployment. And so this kind of spans, and it's a cyclical effort. You start with the data collection, data processing, you go through and you get a certain model, and it's okay, and it's pretty good. But then you refine, and you say, well, let's add what we now have found, and what new information we've learned, we encode that in aerial photos, and then we'd go through the second pass. So this training is just going through the circle really the first time, the one traversal. So there's lots of room for improvement, but let me walk you through the code. Okay, so I'm going to take you first to the GitHub location. So if you go here to GitHub, Intel Software/Jurassic, this is where I'm keeping the repository for the code for this. And it has the preparatory steps where you can actually also get the aerial photo data set that we use to create the model. And so if you wanted to go ahead, you could download the zip file for this. I'm going to show you later how we can do a git clone. It's in some of the instructions that we do. There's over 12 notebooks here, but there are 12 principal ones. And some of these have little offshoots that you can go down a left path or a right path, depending on this is, for example, a case where we were training on an Intel Next Unit of Compute. This is where we were actually building it on a server. And so there's different minor little branches within, but essentially it's 12 notebooks. Now, we're not going to go through all 12. I'm going to highlight some of the more important ones, the salient ones that we think are necessary to drive the point home. But I just wanted to show you where the code comes from and how you can get to that repository. And then this is how you clone it. So I told you that I would show you how to do the git clone. Basically, after you log on to the dev cloud using those links that I showed you, you will arrive at a certain location in a Jupyter notebook. And I'm going to show you how to drive that. But these are the instructions. They're encoded here in the Git repository for what you need to do to prepare if you are on the dev cloud or whatever. So the first thing you're going to do is get the code. Then you're going to CD into that code, and you're going to do a certain set of operations to ensure that we're using the proper kernel, for example. And then this is how we would download the data set. Now, if we're on the dev cloud, the data set's already there. If you're on your laptop or someplace else, then you could use a wget in the following way from Dropbox to get that data. So those are just some of the notes. Now, when we get to the OpenVINO section, there's going to be some additional preparatory steps that we want to do. And so we'll be covering that later. So this is the code. And so what we do is we log into the dev cloud. And when you log into the dev cloud, you're going to see, probably something like this screen right here to start with. This is the launcher. And so the launcher will come up, and you may not have custom kernels like I do here, but you'll have some of these blue PPT kind of things and the orange PPT things. And if you're prompted, just go ahead for now. If you're prompted for which kernel you want to use, go ahead and choose the Python 3 kernel if a little pop-up comes up and asks you. If it doesn't ask you, don't worry about it. The notebooks will self-select the kernels that it's interested in. But if you follow the instructions from the Git, you should have a folder structure with a Jurassic in it. And if you open up this navigation panel over here on the left in the dev cloud, it's kind of a Jupyter hub kind of an interface. And so you can see your folder structures. This is where we're going to be stuffing the models in this folder. We're going to be stuffing our data right here in the data folder. We have various images in the assets folders, things that help inform the notebooks and provide some graphical interest. And then the results of our data, our experiments, our metrics and stuff, we'll stuff here into the results. Primarily, we're going to be focusing right now today on the chapter 2, which is the context and clustering and why that matters. And so we'll be showing you a little bit of that. I may go into just a little bit of acquiring the aerial photos to show you how you can collect your own photos. And then we'll jump right over into the training, and we're going to choose, building and training the PyTorch model, the ResNet 18 model. We'll spend a little time with that. I'll probably have my friend Rahul cover that in more detail. And then after we do that, we will be set to go back to the slides and have Raymond walk us through all the cool things that OpenVINO does to optimize the model we just created. And then we'll do a code walkthrough of chapter 9 right here using OpenVINO, so you can actually see it, doing its thing. And then we'll go ahead and probably do this heat map where we actually generate the map that we could take out into the field and put it on our phone or whatever we want to do. So that's kind of an overview of where we're heading. And so let's jump, first of all, into chapter 2, dealing with context. Now, if you remember from the video series, I emphasize that context is very important in geology, and in finding dinosaur bones, context is critical. You can pick up a rock and think that it's a dinosaur bone, but if you're picking up from the wrong context, if you're picking it up from something like some quaternary depositional place, nowhere near where there were Mesozoic sediments, then it's not very likely that what you found actually is bone. And so context really matters. Context matters in the global view from that perspective. It also matters in the very local view, as I've described. You can be finding all kinds of bone fragments and you don't have a clue. And no paleontologist on the planet would probably be able to look at some of these fragments and tell you what dinosaur it came from until you find the key. You find that claw, you find that tooth, you find that certain vertebra, you find certain diagnostic bone pieces that then indicate what that dinosaur is. And it could be diagnostic down to a species level, maybe the next level up at the genera, or it could be at the family level. So many of the things we find, it pins it down as being a sauropod, a long-necked dinosaur, or a theropod, which is from the Jurassic, the big two-footed meat eaters. But the more specificity we can get by finding certain specific diagnostic bones, and we can narrow that suspect list down, considerably. So context matters. And so, when you first go out and you start collecting this data with your GPS, many times you don't know what you found. You found a fossil and you think it's bone. Okay, so flag it as bone. Okay, type in, found bone fragment. But over time, you collect maybe thousands of these waypoints, as you first are learning. And then what you begin to find is that if you were to cluster them, you don't know what each cluster is, but you know that there is a cluster. So maybe there's a group of fossils down here. Maybe there's another group of fossils over here to the right side. And maybe there's one or two clusters up in the left. Now, this is some synthesized data here, but it has no color to it. Like, it's just data. And so what you do is you use clustering software to begin to say, well, how many clusters do I have? And where are they? Where do they start and where do they end? And this is where you could use something like k-means, or you could use something like dbScan to identify where the clusters are. And that's important because once you identify what the cluster, that this is a cluster, now you can go back and take photos and videos of the coolest bones from that cluster. And then you can take those back to a museum or to a paleontologist at the university or on a fossil forum and say, what is this thing? Look at this picture. Look at this video. What do you think? And now you can begin to identify and label what those clusters are with the help of experts, right? And so, again, this is just talking about why context matters, and I explained that in another video. I just did want to say, we're going to be going through using the Intel AI Analytics Toolkit and its umbrella of libraries that sit underneath it, as well as the OpenVINO toolkit. And so we're going to be using various key sort of suspects here in that portfolio of libraries. For example, in this unit, we're going to be talking about the Intel extension for Scikit-learn. And so we're going to be using Scikit-learn to do a lot of this clustering stuff. Sometimes Scikit-learn can be a bit slow, and particularly when we have larger data sets, it can be slower. And so the Intel extension for Scikit-learn is part of this portfolio of faster, optimized, and sometimes significantly faster. It could be, 1.4x to 1,000x, depending on the data set, depending on the nature of the data that you have and how much data and so forth. But it can be incredibly fast to use an optimized version, and so we'll be showing you how to do that. It takes 2 lines of code. But I just wanted to introduce you a little bit to the overall view of the software we're going to use. We did have a review of some of these in some of those videos in the series. We covered a little bit about the Scikit-learn, Intel extension for Scikit-learn, a little bit about PyTorch, the Intel extensions for PyTorch, a little bit about OpenVINO. But there are other things that we've accelerated. We've accelerated NumPy. So if you use those aggregate functions, the ufuncs, the aggregations, reductions, fancy broadcasting, slicing, and so forth, you can get incredible speedups, because underneath the hood, you get rid of a Python loop, and instead you call a function that's been optimized in C, basically using the math kernel library, the Intel math kernel library under the hood, which is part of this suite. And so these things really speed up. We have accelerated versions of XGBoost for TensorFlow and so forth. So I'm not going to go into all of those, but this is just an overview of these. And where we're going to be playing today, more specifically, is within the AI Analytics Toolkit. And we'll be covering some of the deep learning stuff. I won't be covering Neural Compressor or the Model Zoo or the TensorFlow today. I'll be focusing on Intel optimization for PyTorch. Let me just explain a little bit about that, we put all of our optimizations, we upstream them to the stock versions of TensorFlow and PyTorch and so forth. But their cadence at adopting those independent groups is slower than the rate at which we create them. And so our toolkit represents the latest, greatest, fastest aggregation or grouping or AI analytics toolkit, waiting, for when those other groups, PyTorch and so forth, adopt these changes. And so there's really goodness in just using the stock versions, and we have many of our optimizations already in there. But I'm using the toolkit because I want even more. I want our latest, greatest optimizations. And so I use the toolkit. We're going to be focusing on that a little bit later today. We're going to be focusing on the machine learning parts, not so much on XGBoost that we've optimized, but on the Intel extension for Scikit-learn. And so we're going to be showing you how to do that. And I won't be covering the NumPy, the SciPy, Pandas, Numba, the data parallel Python or the Intel distribution for Python that we have. I won't be covering that explicitly or any of these others, but I wanted to let you know where we stand. And so what we're talking about here is just why the Intel extension for Scikit-learn can provide these really amazing speedups, depending on your data. So just the way we read this, for example, we have dbScan, and for different data sets, 500,000 rows and 10 columns, just as for doing training. With respect to the stock version, we get a nice accelerations. And dbScan with 500,000 rows and 3 columns, dbScan with 500,000 rows and 50 columns, so it really is dependent upon the data. But this is showing the times for doing a fit function, the training for Scikit-learn. And k-means and KNNs and logistic regressions and linear regressions and principal component analysis, ridge regression, a random forest, the support vector classifiers, support vector regressors. We have all these things. So this just shows the goodness over the stock versions when you use those extra 2 lines of code. And the same thing for inference. Now, inference, you can get some really whoppers of accelerations out of these things, depending on the data set, again, the nature of it. And so you can look at 250,000 rows, 16 columns, 10 clusters for KNN and so forth, and see how the optimizations do over stock. So this is just why. This explains the reason why I want to show you this stuff. And so as we go into this, this is really just showing, we're going to create some blobs like I showed you, those clusters. And, this is how we actually create that gray blob of stuff here. And so this is simulating what it's like when you collect all those waypoints. And for example, for us, we've been out in areas in Cretaceous deposits, not Jurassic deposits, but we've been in an area where we found Jurassic deposits like here, and then just a mile or two away, we found Cretaceous deposits over here. And then in some other part of the state, we found other deposits where we had, crocodiles and stuff out here, 6,000 feet in elevation in New Mexico in the desert, but we're finding the evidence of those crocodilians. And so, but let's say over here in these areas, this is a Jurassic deposit, and maybe over here was a Cretaceous deposit. When we're looking at those Cretaceous deposits, what we find is evidence of this seashore. And so we find shark's teeth at 6,000 feet in elevation, shark's teeth, definite shark teeth. And but we also find some bones. We find dinosaur bones as well. And so sometimes this clustering gets a little bit convoluted. Are we dealing with shark teeth? Or we know that we found a vertebra that would be similar to a plesiosaur, kind of a long neck swimming kind of a looking thing, kind of looked like a dinosaur with fins. And so, so helping to cluster this could help us to begin to say, okay, well, we're finding the shark teeth more on this end, we're finding the dinosaur bones more on this end or whatever. So this is why we start this process, right? Okay, so here's some of the code that we're going to use. So this is where we apply the code for patching. And so what I'm doing here is I'm establishing a listener. And so I'm saying I'm listening for any opportunities to accelerate scikit-learn algorithms. It doesn't accelerate every scikit-learn algorithm. We've only optimized maybe 30 or so, but I'm listening. And so when we import k-means from scikit-learn, this listener says, hey, we have a fast version of k-means. We'll use that one for you. And so it's going to use the fast version of k-means. Now, here we're just taking that blob data that I created, those gray dots. That's my data X. And I'm going to do a fit using k-means to that. And then I'm going to just do a scatter plot showing colors based on the clustering that then occurred. Basically, the clusters are encoded in the labels, in the k-means labels. And so I can plot those now in color. And so k-means actually established a color code or a category, a clustering grouping for identifying a cluster. And I said, look, I think that there's 4. It's kind of a Rorschach test, but you just say, oh, I think there's 4 clusters here. And then it says, well, if there are 4 clusters, this is how I'm going to paint them. And so now you can begin to see the delineation of, if you find a bone here or here, which cluster is it in? If it's right here, it's probably a green one. If it's over here, it's probably blue. And so this clustering can really help with your labeling efforts and being able to get help from experts to identify what some of these representative samples of fossils might be. And so now that you've done that, now I got to say that this is kind of a stochastic thing. Every time you run k-means, it's got a random seed. It'll give you a different view. It'll seed the initial centroids in different locations. So the clusters may not come out exactly the same way. Sometimes it may color this one the same as this or whatever. It could do, it's going to be a little different every time because it's not deterministic, it's stochastic. And so if you wanted to be deterministic, then what we would do is we could do this as a classification exercise now. Once we've clustered it and we've taken it to these experts and say, what are these clusters? I've got this bone and this fossil and this tooth and these things, and we get some expertise, then you can begin to say, okay, now that means all these other things over here have a higher likelihood of being those things. For example, in this picture, this is a picture. It's the one place that you can actually see this in an aerial photo. You can see these bones. There's a large extent of these bones. You see that elephant hide looking soil? That's that claystone. This happens to be a grayish looking claystone. It's all broken up like popcorn. But then these dark pieces, every single dark piece you see there is part of a dinosaur bone. And it's eroded and it's just crumbling into dust now. But these bones were at one point articulated, bones, and they're crumbling away, from erosion. But you can see it actually from the air. It's one of the few times, the only one I can even think of, where you could actually see the bones from an aerial photo. Normally you cannot. And so our AI does not rely on looking for bones from the air. It's looking at the depositional environments. I want to emphasize that. But this is the one place where you can actually see the bones from the air. And what this means is, when we first came up on this, you pick up this little black thing here and you look at it and say, well, looks like a fossil, but I don't see the osteon patterns. I'm not quite sure. Maybe it is, maybe it's not. It's got some long grain, but it could be petrified wood. I'm not sure. And then you continue to pick these up, and then you pick this one up, or this one, or this one, or this one. And now every larger chunk that you pick up is obvious bone. You see the osteon patterns, you see long grain structure. It's like it screams bone. And so by inference, then all these darker pieces were just broken off, and they just don't have enough meat on them for you to be able to see, and without a microscope or something. But yeah, sure enough, all these things are bones, and we know that through this context, right? And so context and clustering are kind of holding hands. And so now what we do is we will cluster that same data, that same X data. And now that we know what we're looking for, we can label them. We can have a training set and a test set and say, well, these are, a certain category of entity. Maybe this is shark teeth. Maybe this is alligator scoot, crocodile scoots. Maybe this is from a fish. Maybe we find shark teeth, or maybe we find alligator gar type fossils. Ancient Cretaceous diamond pattern scales. We found those kinds of things, or maybe it's dinosaur bones. Maybe it's like a partial frill that we found from a ceratopsian, an early ceratopsian that we found, and kind of part of the nose cone of the nose. But you can begin to label the known things, and in this case, we're going to just use support vector classifier. Now, I've already patched from before, but I could say explicitly patch just the SVC algorithm. If I don't want to patch everything, I can just be very surgical. And so then I do support vector classifier just as normal. In this case, I did the import, that's one line of code. I do a patch, that's 2 lines of code. And now we'll get the fast version of SVC. And so with SVC, you use it just as normal. And so, I'm going to use a standard scalar, set gamut as auto, do a fit function right here, and just go to town. And so now now we're classifying it. And so now I have a more deterministic way of saying, well, if I find a bone here, it's probably going to color it blue. If I find a bone here, it's probably going to color it yellow, and so forth. And so those colors may have, like I said, maybe it's crocodilians, maybe it's shark teeth here, maybe it's, Camarasaurus bones here, from the Jurassic, and maybe these are Cretaceous things up here, whatever, right? And so it depends on the geographic scope of how big this map is. This could be a very local thing, right? It could be very local, where you're finding a Camarasaurus related bones here, teeth and femurs and stuff. And maybe over here, a few hundred yards away, maybe you're finding the Allosaurus claw or whatever. And so these things tend to be more related to Allosaurus. Sometimes it's not that way. Sometimes in these river deposits, many different species of dinosaurs were wiped out together, and they just got tossed down the river channel, and it was a jumble. But so clustering doesn't always work, but this is how you do it. And then this is just kind of a nod to what we tried here with the kernel density estimator. This is, okay, great. If I find something right here, I know it's a bone. If I find something right here, I know it's a bone. But I can show you places where we found definite bones, here, 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 and here. What do I say about the places in between where I didn't happen to see a bone? But I'd like to give it a number, and so this is the way that we go about that. So, what we're going to do is take our data, we're going to stack it in a certain way. So, and I would recommend too, there's a book here by Jake Vanderpla, Python Data Science Handbook. Awesome. If you ever get a chance to watch any of his videos at PyCon, I think he's a prof up at University of Washington, if I'm not mistaken. Brilliant guy, great books, great videos. But this is applying his techniques of doing the vertical stacks and then calling the Gaussian kernel density estimator, which we did not optimize yet, by the way. But I'm just going to show you what this looks like. And so now with that same set of blobs and that same set of clusters of data from the X data that I was showing you, now I get a sense. So you see, I didn't see it in the cluster graphs because there were so many dots piled up. You can't really get a sense of the density. But here, we can get a sense of the density. And we can see that the two largest clusters were down here in the lower bottom left, and then in the upper left. And then there were two other clusters that had some bones in them. But what this begins to help us do is to say, well, then, what if I find a bone way over here? What is the likelihood that it even is bone? Now I can assign a value to that. If it's in this blue range here, I've got a contour map that tells me, what the probability is. So even if I do or I don't find one, I have a probability of bone finding within this, okay? And so this is the idea of the kernel density estimator. And we use that to do semi-supervised learning so that when we find a bone, we know it, we flag it, and we know exactly what that label is. If we go off to the Oregon coast where I know there's no dinosaur bones, and I could take a waypoint and say, definitely no bone here, not going to happen. Go to the middle of Los Angeles someplace, away from the tar pits, and look, and those weren't dinosaurs anyway, but yeah, definitely no bone there. Someplace in Iowa, okay, definitely no bone there. That whole big map that I showed you in the Morrison, if it's not in a red dot area, I feel pretty confident in saying there's no bone there. And so I have no bones and I have bones. But what about those regions nearby the bones? And so this is what helps us label aerial photos in nearby areas to places that we have found bones. How do you call, if I found bone right here and I've got an aerial photo for it, yes, I found bone there, cool. And then I just scoot the image over and take another shot of an aerial photo. Well, do I say that image has bone in it or not? Well, if you say it's no, you're putting it way down at 0. 0 is a very powerful number. 0 means none, okay? 1 means, yeah, we definitely found it. Well, there's an intermediate case. And if you're in an area nearby where you found bones, you don't close your eyes. You keep your eyes open because there's a possible discovery right at your feet. So you need a way of describing that. And that's why we use semi-supervised learning for this. And then we're just going to go, we normalize the peak. So the highest peak I'm going to say is a probability of 1. And then we just, just playing with the numbers now. But this is just a check of the k-means acceleration. And so in this case, for this particular data set, I was getting about a 3x acceleration from using the Intel extension for Scikit-learn rather than the stock version. And so this is what we do with context and with clustering and with classification of tabular data for your waypoints. Okay, so I've skipped over several of the units. They take a bit of time to develop, but the code's there. You can analyze it, and it's not too complicated. But what I did want to do is, many of you may not be familiar with acquiring aerial photos. And so what I've done, I've used both Google Earth, and now I'm using Google Earth Engine to grab and acquire these aerial photos for academic purposes, for teaching, okay? And so for that use, we're good to go. You can also use Bing. You can use the U.S. Geological Survey has aerial photos and so forth. And so I'm using aerial photos, not satellite photos. Satellite imagery tends to be even some sub 1 meter resolution, tends to, in my view, not be enough resolution to look for the kinds of things I look for, anyway, when I'm looking for good dinosaur hunting locations. I need to see those colors and those textures down at a sub 1 meter resolution. And so, it'd be equivalent to flying over at a few thousand feet, maybe 10,000 feet in an airplane. And it turns out Google Earth Engine, while it does have satellite imagery, a lot of satellite imagery, you can also load up aerial photos, and that's what we do. And so I wanted to show you how you do this. And so it will require that you have a account with the Earth Engine website. And I'm going to go ahead and launch this. Now, I've already loaded some of these things in here. I'm going to show you how they work. It's just a little bit of JavaScript code, just a small smattering of JavaScript code. That JavaScript code I've shown you what it is right here. So you could just copy this JavaScript code, and in your instance now of Earth Engine, you could paste that code right up here. And then what we're going to do is we are going to run this code. And so when I run it, now I can expand it so you can see what you're looking at. This is Dinosaur National Monument near Vernal, Utah. And we found a lot of bones here. And we found some actually, obviously, I mean, there's hundreds of bones. They've been digging at these bones for over a century or about a century. But they're in this brushy basin, Cedar Mountain Formation intermix right here in this band that goes left and right kind of in this area. And you don't tend to find the bones very much out here, and you tend not to find the bones very much up here. It's in this, this is called either a syncline or an anticline, where the strata were like this and they tilted like this, and they're at a very steep angle. And what we're looking is down that angle, and the house is sitting up here. The little protected monument here is sitting on top of that, and they're digging bones right out of the rocks there. But we found bones way over here on the right as well, just walking around and looking. You're not going to find bones down here near the river. And so this gives you a sense. But what we could do is say, well, let's say that we know that there's bone here. Then I could use the snipping tool. And then I can just snip, and I can just click and drag from the upper left corner down to the lower left corner and snap it. And then I can save that as a file. And I can just do this repeatedly. Now, that's a little inefficient. But if you want to get started, that's the way you can test your test this model against areas near where you live. Or let's say you want to go to Portugal and help look for that dinosaur that was found there in a Jurassic sediment similar to the Morrison. May or may not work. I actually had a little bit of success even doing that, and I'm not even kind of don't believe my results there, but maybe it got lucky. But so you can near Pombal, Portugal. Mainly, this was trained on the Morrison of the Western United States. It was trained actually literally on New Mexico strata, which for the most part, we do have one syncline, but for the most part, those sediments are horizontal and not like these syncline things that are tilted up. So the data distribution is a little bit different, right? The probabilities are not going to be, it's not the same distribution exactly. Nevertheless, it worked fairly well. But this is how you can acquire the images. And so it's just a little bit of JavaScript code that you can use. You can snap it, and off you go. And you can do this for 10, maybe 50 images of things that you want to test and go to town. But that's how you do it. Okay. And so now we're going to go back over here to the next unit, which is how we are going to train and develop this model, this ResNet model, and how we're going to use, so we're using PyTorch, and then we're going to sweeten the pot with the Intel extensions for PyTorch.
Hey all, I'm Rahul Nair. I'm an engineer at Intel. I focus on AI architecture and working with early stage startups, helping them optimize their workloads for Intel's architecture using oneAPI to scale it even beyond Intel architecture. In this session, we are particularly focusing on training of an AI workload using PyTorch and Intel optimizations for PyTorch. Like you've seen in the last session, we have the dataset ready with three classes, 0, 1, and 2, based on if there's no bone, it's a 0 class. If there is, maybe there is a bone, the class would be 1. If a bone is highly likely, it's 2. So we finished the first part where Bob covered with active learning, where you were labeling a data set which inherently didn't have any labels, but based on how the dataset looked like, you labeled it really fast in the session that Bob took you through. Right now, we have a really cleaned set of data with 3 classes. We'll use a simple PyTorch classifier to train a model using this data with the 3 classes, and just see if our PyTorch model is able to classify a new image based on, if you're giving a new satellite image, if it's 0 class, if it's 1 class, or 2 class. Let's see. All right, so before we start, it's always good, especially on Intel CPUs, and if you're using PyTorch with Intel's parallelization libraries like OpenMP, to setting these three environment variables. Like you're seeing, we are setting the OMP num threads, KMP affinity, and KMP block time. So OMP num threads, let me give you maybe a two-sentence explanation of why we are doing it. In PyTorch, specifically on CPU, for parallelizing different workloads, if you're doing multiple convolutional operators, or if you're splitting a huge PyTorch graph and running both graphs parallelly internally, it uses a library called OpenMP for CPUs to parallelize these operations and to configure the number of threads that these libraries can use. We use things like OpenMP num threads. And KMP affinity and KMP block time is specifically for when you use Intel's version of OpenMP. You could install it if you're using conda install Intel OpenMP, or even pip install Intel OpenMP. Specifically in these libraries, you get further few more optimization opportunities, where if you look at KMP affinity, you're setting something called granularity equal to fine, compact 1, 0. Essentially, what this means is that we are telling PyTorch to use to essentially bind one thread per one core and start from the zeroth core. That's where the zero comes in, and also allocate these threads in such a way that core zero has the first core, core one has the second thread, and like that, so that you have these threads bounded together very close to each of these cores. The reason is that many of these workloads, the high compute workloads that we're working on, if there is some sharing happening, we don't want these threads to be running on completely scattered, with the first part running on core 0 and the next part running on core 56. We would like ideally to have all these threads running together, one core after the other, and we don't want more than one thread to use one core, because we are doing things like matrix multiplication or convolutions, right? And anyways, even one core would be using the floating point units of the CPUs fully. So we don't want two or three cores to sort of compete to get the floating point units to run its workload. The one thread itself is using fully the floating point unit. So it's okay to just set one thread per core, and to set all the threads to use cores that are very closely laid out. That's what this basically the set environment variable does. After you set that, you can see this is I'm running on my local machine. You can see the OMP num threads is 14. I'm setting a random thread, a random seed. Also import all the other things that's required. Here we are importing torch, and we are importing one of the key libraries for optimizations, like Intel extensions for PyTorch. I'll talk about why we are importing Intel extensions of PyTorch and what's the difference between Torch and PyTorch in about in some time. But these are the two main libraries that we need to import. And others are the regular libraries, to plot a graph. I'm importing Seaborn here, Torch Vision for data loaders and things like that. Let's see the version of Torch and PyTorch, Torch and IPEX. So this is very key. The Torch version and IPEX version to match. If you're installing IPEX for 1.13, it expects that the Torch version is also 1.13. Here it's 1.13.1, so it expects Torch version to be 1.13.1. So the difference between Torch and Intel extensions of PyTorch, right? Intel has been contributing to PyTorch for a long time. If you see the total number of commits Intel is probably the third or fourth biggest committer to the open source PyTorch project. So a lot of optimizations has been gone through to make sure that PyTorch works really, really fast on Intel hardware and varied hardware. In a way, the optimizations that Intel has, PyTorch makes it really competitive on any x86 platforms. Even the oneDNN, that is a neural network accelerator library that is specifically designed to run on Intel CPUs. That's a default in PyTorch. You could just, if you're running PyTorch on CPU, even if you're using a hardware GPU, a dedicated GPU, chances are high that you're running some part of that PyTorch using oneDNN, and the oneDNN acceleration is from Intel. What is the difference between IPEX and PyTorch is that there are further optimizations that we make and support for newer hardwares like our Intel discrete GPUs. That first comes on Intel extensions for PyTorch. And because of the cadence difference, right? PyTorch has a different cadence once in 3 months or so. I forgot what is exact cadence of PyTorch releases. Sometimes you don't, if you want the best optimizations right now, right? Because IPEX is a library that we control completely, we can release the latest optimization faster there, which will eventually come to Torch. But if today you're trying to build a model on an Intel CPU or x86 architecture, you want the best optimizations. Then you can definitely install Intel optimizations for PyTorch and use as oneAPI to get the best optimization out of there, or you can wait for a couple of months when the next release of Torch is coming out, which might have these optimizations already merged. We are still continuing to merge a lot of optimization to mainline PyTorch. Just IPEX just makes us easier for us to release the newer optimization faster. So for some of the folks out there who really want the latest and greatest optimizations today, they can just try out IPEX and get the best performance out of the box. I'll also show you how to use IPEX and what are the changes you have to make. It's essentially one line change, but I'll go through that when we are going to the training part. Specifically on this workload, right? Like I mentioned, here we have a really good data set with 3 classes, 0, 1, or 2. What we are going to do is that we are using a pre-trained model, and we are going to do something called fine-tuning to fine-tune the different layers of the model to get a new model that's tuned to the data set that we have. Here we are using a model from the ResNet architecture called ResNet 18. It's very fast to train on a CPU. It will only take a couple of minutes for you to train a really good classifier on a CPU using this approach. What you do is that you download the pre-trained model, the ResNet 18 in this case. You replace the last layer, right? If you can see here, the output layer, what you do is that the default output layer for ResNet is like 1,000 classes. That's how the model was trained. So we remove that output layer, we replace it with a 3-layer in our case, where we want the model to classify 0, 1, or 2. The advantage is using a pre-trained network is that the layer 1 to a couple of layers like layer 10 or even to layer 17, it has learned already to sort of identify the basic structure of an image, understand edges of the image, and do sort of basic level classification tasks that if we were to use a brand new neural network, we'll have to train it for a longer time for that different layers of the neural network to learn that. So here, essentially, we just have to take a pre-trained network, just tweak it a little bit to essentially understand the data set that we are giving it, so that it can classify it better. So it's much faster than just training a neural network from scratch, and it's really ideal for if you have a CPU to use fine-tuning approach. It's essentially becoming a standard. Even if you look at a lot of Hugging Face models in a lot of these transform models. There are fine tuning is you could call it a standard. There are things like prompt tuning that's where you don't even need to train the neural network. You just tell the network what to do. But I would suggest if you have a new problem statement, either in Vision or NLP, start with a pre-trained network. Then just remove the last layer, try to fine tune it. If it works well and good, so it saves a lot of time where you don't have to train the full network from scratch. Before even starting the training, let me set environment variables for everything. It's a good practice because when you're running the workload and you want to share your result to another person to try it out, or if you want to run it again several times, it's good to try to control the randomness in a way. So these are the couple of variables that you set, like the setting the random seed of NumPy, setting a random seed of Python, and random seed of Torch. This doesn't complete the entire randomness because inherently neural networks there are some randomness associated with it, but this brings it very close where you could expect to see similar results in benchmarking and things like that if you're setting the seeds correctly. So I'd always recommend setting the seed when you're doing a when you're building a workload. So I'm setting a seed. I'm just giving a value 9342. Now let's come to the data loading part of this. So essentially, what we do is that we are taking a REST 18 model. So I'm using the same REST 18 model ImageNet stats. These are the stats that the ImageNet team has recommended to use for using any model that's any model that use the ImageNet dataset to train. So it's essentially the mean, standard deviation, and such values. I'm using that. And we are doing some small transformations to our images. We are doing a horizontal flip, random rotation, then just converting to tensor and normalizing using the image and stats. When we try this workload, initially we even tried to do a Gaussian blur, but we found out that doing a Gaussian blur on this data set gives you very varied accuracy depending upon the randomness that you set. Then when we thought about it, it sort of makes sense, right? Because these are satellite images we have, and if you're doing Gaussian blur, it sort of acts like a spatial difference where some images might look like it's taken from a distance one distance A, another image is taken from a distance B. So that was really affecting the accuracy of this model. So it's very important when you're doing transforms for your data, be it image, be it NLP, to see if the transforms you're applying can really help you, or if there are transforms that can hurt. This is an example where we thought Gaussian blur would be a no-brainer, which the default in a lot of tasks it really helps, but in this task it didn't really help. So that was something that forced us to think on what sort of transform that we should really apply. It's a good thing for you to also think about. So I created the transforms. Now let's load the dataset and let's apply these transforms. I'm going to load the dataset. I have the datasets in the data directory. So I have it in a directory called 3 class manual removes, where I have cleaned up the dataset with 3 classes, like I mentioned, with both train and validation dataset. I have loaded the data. So I have in train data a set of images with 3 classes, validation data with, again, a set of images with 3 classes. Let's first find out the data distribution. So this is a small function that I wrote to just plot the data distribution. Let's plot it and see what it looks like. So before even this, right? So it's ideal if you are working on a machine learning problem to have to not have class imbalances. So essentially, if one class is significantly higher than another class, it might be challenging to train a good model out of that. So it's always good to have similar number of data set for each classes. Here you can see for the class 2, there's slightly a bigger number of images than for class 0 and class 1. When we tried this example, we didn't really see any issue with it. But if I'm going to deploy it for production workloads, I would really want all the classes to be the same, because I don't want the model to be biased to one class. So it's something that you could really check when when you have your own data set. See if you can sort of balance out the classes, so training becomes easier and there are less problems in downstream when you're deploying your model. Let's see the validation classes. The validation also is similar. There's slightly more images. There's around 350 images for the class 2. There's around slightly less than those images for around 250, less than 250 for class 0 and class 1. For our test, it wasn't an issue, but again, I would heavily recommend if you're uh, really doing a production workload, look at your distribution of data, see if you can do, make all the classes the same. There are many methods like duplicating the lesser classes and things like that to make sure that all the classes are the same, um, to sort of reduce the imbalance of your data set. Now that we looked at the class distributions, let's load the data. I'm using a batch size of 128. I'm using a PyTorch data loader to just load the data set for both validation and training. Now it's good to, so the data loader have already applied the transforms that I have showed you above. So these transforms, right? Where is it? Yeah, random horizontal flip, random rotation, and things like that. It's already applied those transforms. Let's just see what those transforms look like, right? So it's loading the data. See, the transforms are looking like it's slightly rotated. There's some clipping on the side. These are the transformations that we made to essentially make it a bit harder for the neural network to learn from these images, because we didn't want the model to overfit. So that one of the things that you could do to sort of make it hard for neural network, in the sense to reduce it to overfit, is to do data augmentation. That's exactly what we did. There are two situations where you normally use data augmentation using transformation. The one is when you have like very limited data and you're not able to get a really good accuracy or really good metrics for your training using the data you have. Then what you'll do is that you'll duplicate a lot of these images. Yeah, you'll do some transformation of image A and create a new image B, and you will use both in your data set. The other situation is where you have a pre-trained model, but one of the things is that you need to make sure you can augment the data in such a way that the model is not uh, um, you know overtrained, or we have a good enough or robust model. In those situations, we can use augmentation. So for validation data, essentially, to reduce, one of the ways to do really to reduce overfitting, but there are other ways like dropout and things like that you need to think of beyond augmentation to see if you are seeing overfitting in your models. In your validation data, you don't really need to do any augmentation, because essentially these are data sets you're just loading, converting to tensor, to check if your model is working as you want. So, like I mentioned, we are using a simple REST 18 to train the model. I have split this into 3 classes where you have a model definition class where you can select different types of resets, like from 18 to 101. There is a metrics class that has some helper functions for accuracy and printing the accuracy and things like that. There's also a trainer class. The trainer class takes in the model and trains or fine tunes it. Uh, for me, this sort of splitting the deep learning solution to 3 has really helped. Where if I want to change anything in the model, I only want to focus on the model class. If I want to change some hyperparameters or some training regimen, or the STD, if I want to shift STD to Atom or any of those things, I can do in the trainer class. Each person might have a different way to do it, but this has really worked for us. And it really, if you're starting new, it really suggest you look at it, and if this works for you, please take this sort of approach. So here there are, like I said, there are different backbones. By default, the backbone is 18. And so if you don't give any particular backbone, it's REST 18 is taken as a backbone. And the last layer of the network, that is a new layer that we are adding, is initialized using a Xavier transform. We have found that Xavier transform gives you the fastest time to a properly built model. Also, there is a simple flag for the model, or a simple parameter for the init function. If you set it as false, what you get is that you get a bigger model. We didn't really have to use it. We only had to change the last layer, and we got good results. But if you are bringing in a new data set and you want to try out the not so simple model, then you could definitely try this. It essentially adds a bit more layers than the last fully connected layer. And here we are setting the Savior transforms for the other layers as well. Coming to the metrics class, like I mentioned, it has some helper functions, essentially to measure the accuracy and to plot the accuracy graphs. Um, just good habit to sort of compartmentalize different aspects of a deep learning model building into different places. Training in one section, model building in one section, and accuracy measurement and tracking in another section. That's why we put the accuracy method in a different class altogether. All right, guys. So we have seen the model class defined. We have seen the metrics class defined. Now let's coming to the third part of the puzzle. That's a trainer class. In the trainer class is essentially where we pass in a model that we had defined, and we can call a fine-tune method or train method. There are some debugging methods also, which I'll go through, that will really help you to see if all the model that you had defined is correct. There is no problem with the model, so that you don't have to come back in a week when you're training a neural network, a big neural network, and see that, oh, you forgot to configure the model in such a way. So there are like really quick things that you could do to make sure that the model they are defined is correct. Let's see what the trainer class looks like. I hope you can see my screen. So in the trainer class, I'm using a default optimizer, stochastic gradient descent default. You could use Atom or any other different optimizers. STD worked well for this problem. I'm using a learning rate of 0.05. It could look large for this problem, but weirdly it really worked for us. Again, that's one of those hyperparameters. I'm sure that if you use Optima or something to tune it, you would probably get a 0.003 to be better than this. But setting 0.05 really worked, and it was really quick, and there was no real reason to change it. You could set the epochs, all those things, the default epochs. It was 10, but I had to do a quick test on my local machine, so I just changed it to 1. But the default epochs is 10, and you instantiate a metric class, the learning rate, all those things. You have a forward pass that just do a forward pass of the model. You pass in the input and get the result, and you essentially calculate the loss and get the accuracy. And this is a function that I would really like all of you to just focus on, and even if you're not using this particular uh, code example, if you're doing other kind of deep learning workloads, and you're doing a lot of training, I'd highly recommend to have a class, or even a method, or couple of lines to quickly check if the model you have defined works according to what you want it, according to how you think it would. What the train one batch does is that it tries to or fit the model using one batch of the data. If you think about it, you have a neural network, and you take the same data, and you're setting maybe 1,000 epochs, or whatever epochs you want. You're sending the neural network the same data for each epoch. If the neural network is not able to learn or improve its accuracy significantly, then there's fundamentally something wrong with the way you have defined your neural network, and you need to make sure that the way you have defined is correct. So that's essentially what train one batch does. It takes a training data loader, it trains a model, it tries to train that model for 100 epochs with the first batch of the train data loader, and it will print out the results. And if you see the results, if it's not improving significantly, or if it's not or fitting, then maybe look at your deep learning model and see if you have defined it correctly. This has been immensely helpful for me, the training one batch trick, and this is something you might not really see in a lot of textbooks, but it's sort of a practical knowledge that you can see, um, in different code bases where people actually do deep learning in production. We have a train function coming to the regular other things. Like we have train function that does a backward prop, and it's essentially the same. It calls a forward function. It calculates the backward gradients. It does a step to update the gradients. There is also a to IPEX function. So um, I don't know if you guys remember a couple of episodes back, I talked about there's an Intel extensions for PyTorch that gives you the latest and greatest optimizations for Intel hardware. So that's essentially what the to IPX does. You don't have to do much change to your code. You have your default PyTorch code, and the only thing for training, what you have to do is that you have to. So IPEX here is Intel optimizations for PyTorch. I have. Let me go back to show you so that everything is clear. So the import statement, I have imported Intel extensions for PyTorch as IPEX. I'm coming back to the IPEX. So I'm calling the optimize function of IPEX, the Intel extensions for PyTorch. I'm passing the model, I'm passing the optimizer and the data type. That's it. So when you do this, what IPEX would do is that if there are optimized kernels that's beyond what PyTorch already has, right, beyond the things that Intel has upstreamed, that IPEX have, it will apply those optimizations to your modules. If you're using our fourth generation Intel scalable processors like Sapphire Rapids, it has dedicated matrix accelerators like AMX for bfloat 16 and int8 optimization. So if you're doing some sort of mixed precision training, you can change the data type to torch.b how you change is that you'll do a bfloat16 and just call the same apex dot optimize, and it will use the AMX instructions that's available on your hardware. So it's incredibly convenient, and in most cases you'll get a better performance, faster, if you're using IPEX. And I just need to make sure that this is very clear. It's not that these optimization will always only be with IPEX. This would eventually come to the PyTorch mainstream upstream branch. It's just that it's faster for us to release here. And there are sometimes when there's like highly aggressive optimizations, which we feel that it's better to have it as a separate repository rather than with the generic PyTorch, because it might not work with all different types of models. All those things would be in the IPEX GitHub repository and with the pip install versions as well. And the GPU support. Today, if you're using an Intel discrete GPUs, you can only get that support using Intel extension PyTorch. So there are many reasons why you use it, but here I'm using it to get the latest optimization for my device. The final thing is fine tuning. So fine tuning is just a helper function that I've written. It calls the train function essentially. As you can see, the cell.train, and I'm just setting a default epochs and things like that, so that and getting the results and printing the result. Just to make it easier, if you're using a trainer class, to just call fine tune, give the train data loader and validation data loader. It will just do the training and give me the result. Let's come to the training. I'm setting it simple to true here. I'm setting epochs to 1 just to show that an example. IPEX is set to true. Dropout is set to 0.05. And I've set a model name so that I can use this model further for inference. I have said that KMP affinity, torch jump threads. If you haven't set these variables before when you started, it's a good habit to set it here. Then I'm just instantiating the model and passing that model to the trainer class. So here in instantiating, I'm passing the model to a trainer class. I'm just calling the fine tune function. So it's training. I'm running this on my desktop. It's gonna take a couple of minutes to. It's not even a desktop; it's a laptop, and it doesn't matter, right? It's a small model. It'll train really fast. Maybe take a couple of minutes to train it, and once it's trained, you could do a torch.metrics plot to get the validation accuracy. This plot is here because I only trained it for 1 epoch. But if you plot it for a couple of epochs, you'd see the training and validation improving. Once it's done, you can save the model as a torch ticked as a state dictionary. Once the model is saved, you can try to open the model. This is a previous model that I have opened, and here is a helper function to infer based on that saved model. You can do an inference using that saved model and get the results. After this, the next session would be how you would use this train model and use OpenVINO to do optimized inference on Intel CPUs or GPUs or different varied devices. So that's all from my side. There are a few exercises here. I'd really love to hear from you. What do you think about this session? What all things that you want us more to explain, and what else type of workloads that you would like us to see a similar session on? Thank you very much.
So let's go ahead and test our model with some of that holdout data that we had. So we're going to basically try to create this confusion matrix. So we'll show you how to do that. So we can do this either with the New Mexico data or the Utah data to do the validation. In this case, I think we're going to validate against what we found in Utah here. So we're going to go ahead and load a model, and we're specifying that we have 3 classes, and so we're going to replace that last layer with 3 classes instead of whatever the default was. We're going to have a location where we save an output image that we care about. And then we'll go ahead and do these transforms. And so, here we're going to resize it so that it's resized down to 224 by 224, convert it to a tensor, and then we do the normalization step. And so, really this is rather straightforward. We're just going to have a way of coloring an image at some point that, choose a color scheme, a red or a green or a blue hue that we could put over a map. So we're defining what some of those things could be, but we're just going to compute the metrics. And so this is all just kind of standard scoring type stuff. So I'm just going to go ahead and show you the result of the classification of the confusion matrix. And what you see here is that for our train set, and this is our validation set, what we want is big numbers along the diagonals and small numbers on the off diagonals. And for the most part, that's what we're seeing. I think we're getting a pretty good specification of the accuracy here. And so this is just a colorized version of that. And so these bold colors right here are showing that our model's doing very, very well. And these are the mispredicts. We've got these 29 mispredicts over here and these 12 mispredicts over here. But for the most part, it's doing very, very well. So this is just to kind of wrap up the validity of our models and so forth. So we're going to go back to the slides and really tee this up for Raymond to take us the next level discussing OpenVINO.
Hi everyone, my name is Ray. I'm a developer from Intel. And my daily job is we call ourselves the AI software evangelist. And today I got to tell you some interesting news, how we actually get the dinosaur bones with OpenVINO. Okay, let's get right into it. Well, I met Bob in a very interesting way. On that day when I was actually taking a plane from California to Arizona, I get a call from Bob. Bob said, I got a way to find bones, but it's not running very fast. Can we make it faster? And here's a photo of me taking that Intel plane going to Arizona. And on that plane, I was like, okay, give me a second. Let me get on the Wi-Fi on the plane and we'll talk. And this is amazing, right? I get to fly and then I get to talk to Bob. But more importantly, I look down to the map. It's like, you're right. It's so hard to find anything from from the third top of an airplane. Where's the bone? Then I hop on the call, get on the Wi-Fi, which is about, barely working. But I'm seeing the first time how we can use AI to look for a small feature or specific way in a map such that we can help solving that problem. Of course, at that time, we took it and we want to solve it. Now let's talk about OpenVINO, because remember Bob had that problem. It was like, this is not fast enough. We can do better. It takes maybe hours to crunch a big map. Can we do it maybe 5 times faster, 10 times faster? That's where we came in, because me and my coworker, Joel, in PRC at that time, knows how to optimize. So we came to that, okay, give me the source code. Let's get started. So we look at this whole, the code and structure. We look at the pipeline. So where can we go faster? It's the inference step. So apparently we have all these images. We want to figure out and classify. It's like, yes, no, maybe. And that pipeline, we call it AI inference. The step where it takes to get the computer to make the prediction can be done very efficiently. Different from training, you need to have really, really a lot of parallel process. This one is more like, okay, let's make a decision. So that's what we call model optimization today. Let's learn how, because with this and OpenVINO, we can run it on your CPU. Of course, you have one. And maybe your iGPU, which is the integrated graphics unit, and then the processor. And then also we can even run it on the new discrete graphics card from Intel. So that's what OpenVINO is good for. So it's a runtime engine that Intel started many years ago, I think more than 5 years approximately. And we use it for initially for computer vision tasks, like what we talk about AI inferencing with a camera, for example. But today we expanded beyond. And why that's exciting is we have a lot of customers using this for example, worker safety and all that. But we also expanded to natural language processing. And this is such a big, hot topic today. And also we supported, I think it's a real-time series. So you have machines, like for industrial use case. We can also have OpenVINO to accelerate this work. Under the surface of, let's say, all this library, we have oneAPI as fundamental, the foundation part. So when you're calling the library, you don't need to learn how the instruction works, but you can just call it and make it work, which saves you a lot of time as a developer. The problem statement from Bob were he got a Python code with a PyTorch model. And to me, it's a great news because I think a lot of you today could be using that today. And with OpenVINO, we take TensorFlow, PyTorch, Onyx, many different formats directly, and then you can pipe it down. What we do is now you optimize the solution, the model, and in a way that you can deploy on different hardware and also different operating system. And that's useful because Bob has friends. If he wants to share this to his colleague, and now OpenVINO will be like a one-shop for him to share the work. So let's talk about model optimizer. So this is one step that you want to get started immediately when you're trying to optimize the PyTorch model that we started with Bob. Why that's important is model optimizer provide you a couple important and useful tools to first, for example, reduce the model size. So on this diagram here, you can see we can define FP32 or FP16. By doing that, you keep mostly the accuracy, but you can reduce the size of your model by half. On the CPU performance, it may not matter as much, but on GPU, this will give you a huge boost on the inference speed. But for CPU use case, in this case, our runtime also does something with the pruning and all that. It will give you a speed up as well. Why that's important is we just run the model optimizer. In no time, we already get a couple X speed up. And we're going to see that from Bob's demo coming up. And that is something I would love you all to try because we have live demos showcasing how this model optimization can benefit you by doing a couple simple steps like here, MO with the input model and get the output. Now, let's move forward because having this model optimizer does, for example, reducing the size of the model, making it run faster on GPU, and also run faster on runtime. But can we do better? Because remember this problem that we're solving, the computer vision problem, we may not need all the precision. Remember we have this floating point that's really big. What if we can solve this problem even more linear? Because we're looking into a probabilistic model of the map, like 99.9% versus 99.8% of probability, seeing this is where the bugs are, may not make a big difference, but on the performance side, it does. That's why we introduced the post-training optimizations, or we call it NNCF, Neural Network Compression Framework. We have data set that actually we have from Bob, and what we do with that data set is, how about we tune our model so that, okay, maybe we only need less precision here to do the same work. What does it mean? It's like, I want to represent 1 to 10, and that's all the category of things we want to represent. Maybe I don't need 10.5, 10.2, 10. That. All those decimal may not be needed to solve this problem. And in computer vision, it happens a lot. Look at your camera today. You know how you have RGB, and each channel is 8 bits. Even your perfect iPhone or today, your JPEG are using only 8 bit per channel, and you can still see a very good image there. So that's exactly why quantization is very powerful and useful, because you can reduce your data type into, let's say, integer, and the computation is a lot easier. And this is supported by OpenVINO with the NNCF tool. All right. And in the tutorial, we're going to show you that as well, how we do that. Because once you have done these two major optimizations, now we open up this pool of devices you can use. Remember, I talked about we want Bob to share this to his friends, like whoever wants to use it, he or she may not have the hardware. Then with OpenVINO, we are a lot more flexible. We don't need the most powerful GPU to run the inference. You can still use a simple CPU and do inference pretty efficiently. And that's where we have kind of device plugin here, where we make the CPU, GPU, or even a combination of these devices to be working together. I was a developer before. Oh my God, it was so much work making things portable across different hardware. And at Intel, we have done this, and then I was very thankful when this tool exists. Lastly, this is an important part of the tool. Let's say you want to give it to not just your friends, you want to give it to your customers. Someone want to use this. You may not even know what the hardware configuration will look like. Then we can even fine tuning it further by, okay, we automatically discover your device, knowing like, let's say I have CPU and GPU, let's say discrete graphics card. And in this case, we can automatically discover and use those powerful hardware we're shipping today. As of, let's say last year, you may not have the discrete graphics card. As of today, we're shipping them in volume. So imagine now your code is portable a year ago and be able to use the most advanced hardware from Intel anytime. So this is the auto plugin feature. So what we have learned so far, by using OpenVINO, you can have ways to optimize your model. You can reduce the size, make it run faster. Now you have this portability to run on different hardware. And more importantly, it will be future-proof. You can use it maybe 2 years from today, not changing the code, and still get faster. All right, enough talk. Let's do a demo. So after this is the instruction how to install. If you really want to try that, follow the instructions, how to grab all these notebooks to give it a try. But more importantly, Bob will show you how he ran the optimized version of his work on OpenVINO on his own laptop. Again, thank you for watching me, and I would love to see what you have done with this or how you like it. If any feedback, come to the GitHub and leave me a message.
Thank you very much, Raymond. This was great. Thanks for that walkthrough. Let's go ahead and walk through the code. So this is the OpenVINO code. And so you'll notice that it's using the OpenVINO PyTorch kernel. That was the custom kernel that we created. The idea here is that we've gone through the process here of creating a bone-finding trained model. We have a model that works, and it's doing pretty well, but it's kind of slow. And so it takes these image files of aerial maps as input. We do some pre-processing, and we feed that to the model, and we got a model. Cool. What we'd like to do is to be able to optimize that model so it can run on, with the same model. We can deploy it against the Intel GPU. We can deploy it on Xeons. We can deploy it on your laptop. We can, whatever you want, and it will have a fast and easy deployment. And it could then create that output likelihood map in a faster way. And so this is just some of the steps that we would use to do that. And just thanks to Zhuo Wu and to Raymond for putting all this stuff together. Basically, we go ahead and do these imports as usual. So we're going to be importing Torch and PyTorch because that's the model. We're going to be importing the OpenVINO runtime right here. And then a lot of the actually interaction we're going to have with OpenVINO is going to be effectively through the command line. We have a Python way of controlling it, but you could actually do all this stuff from the command line. You could say MO, for model optimizer, and give it some details on the command line and have OpenVINO do it that way. And so we're going to show this how you approach it from this notebook. And so right now what we do is we take the models. We have this base model that we're going to be playing with. And then we are going to take that base model and we are going to convert it to an Onyx model first. And then, so Onyx is kind of a way of taking any model and kind of having a common language or a common model, irrespective of its origins, that you can apply. So Onyx models are very portable in a sense. And then what we're going to do is we're going to, and we'll probably get some acceleration from that one, but then we're going to explicitly do the intermediate representation path where we're going to create a model that is really fine-tuned for the OpenVINO. And so what we're going to do here, this is the ONNX model conversion. We start with the Scratch model, which is ResNet 18. We do replacing that last layer thing again. We can load the data in from the state dictionary if we want. We can do all these things. We can determine whether ONNX exists or not. And then what we're going to do once we have an ONNX model is we are going to convert that model to the OpenVINO intermediate representation format. And here's basically the command. Now, again, this could be done just on the command line. You know, I can go invoke MO. Now, for me on my system, the way we've configured you guys for this lab is the MO command is in a bin folder in the OpenVINO PyTorch environment. And so I'm just saying mo dash, we give it the input of the model that we have, and then I give it the input shapes. I tell it that I'm looking for floating point 16, and then I output it. And so this is really the result of that command when we run this. And so this is what the outputs look like. This would be what it would be like if you typed it on the command line. And then now we're off to doing the intermediate representation. And so here we get this result, and now we can print that we actually have the IR path. And then we will now that we have all these models, we can run inference against the ONNX or the IR format, and we can show the results. And so our input size is 224. Again, we're just resizing. We're not rotating or doing anything weird. We are normalizing the data. And then this is just kind of defining what we're doing. And then we open up the image. We do the transforms. And then we run the inference on it. And so what we do is we read the we instantiate core, and this comes, I think, from the OpenVINO. And then we just say, core, read the model. In this case, we're going to give it the ONNX model. And then we're going to compile the model, and we're going to specify. Now, we can specify over here the CPU, a GPU. We can specify auto, so it could detect, where you're at. And so we can specify explicitly what we're going to target. And once we do that, it's compiled. It's a compiled ONNX model. Now we can get that output layer, and then we can run the inference on that model. So now we can give this model, this optimized model, a test. We can give it a test image, to see what it does. And so then we can compute the results. And so this is the inference for running ONNX, and the three classes it gave are this. So if you did a softmax here, you would see that this is a most predicted class 0. And so here's where we're going to do a softmax definition of that, do basically what I just said. And then we're going to give it the class names 0, 1, and 2. And so now in this particular case, we're going to see that our score, it said that this is a 0 class. It's a no bone entity. And it gives us the confidence level that it's pretty doggone sure, 99.998% sure that it is a 0. It's not a bone. And so now we can run the same thing with IR. So instead of using the ONNX, we can use IR. We give it the same model. We're going to do the same thing. We're going to read it. We're going to compile it. But this time we're saying that we want the IR path. Okay. So that really it's the same as what I showed you before, but now we're going to be computing for IR rather than the ONNX. And so again, it predicts the same thing. I think even exactly the same confidence levels. So the confidence levels are slightly different. But so anyway, and now we can compare the scores. And so, we can give it another image, and this image, it scores as a 1 with a 100% confidence level. And then we can do the performance comparisons. And so we'll give it 400 images, and we'll just run through and calculate. And so what we're seeing here is on this particular model, my frames per second for my ONNX model was about 191. IR was a little bit higher. It was actually the ONNX model came in at 190.75 frames per second. The IR model tweaked it out a little bit more. We got 191.25 frames per second, as opposed to the crude PyTorch model that we did before, that we started with, which was about 82 frames per second. So we've roughly doubled the number of frames per second by doing this optimization. So this is any of the results of the inference on the image folder and the map merging exercise. So this was on an older style of map that we created, but we can basically score the single image, we can score the torch image, we can create a function to take that result to a map. And so we're just going to composite using red, green, blue, and alpha channels. We've got a green, a light green, and a black, and we're just going to give it, we're going to have save it to a file map, and then we can composite those maps together. And so what we're going to do is we're going to just take a look at these maps and create a folder, the 224 map folder, and we'll save that map. We're defining a function to save the map here. And I'll show you what the map looks like. That's really the punchline, is that we run this inference. I'm not going to go into every line of code. It's going to be silly. But we take this code, we run it. I should have suppressed some warnings here. But this is how long it took to do the scoring. This is the inference time, actually, that's going on. And this is the bone map that we created. So what we did is we scored you'll see some tiles here. Like here's a good square tile right here. And so what we do is we take the image, the aerial photo. This represents a 224 by 224 pixel. That may be 300 meters by 300 meters on the ground, something like that. We'll take this image patch and we'll pass that image patch into the model and say, well, what is it? If it's a 0, color it neutral. Just don't give it any color background. If it's a 1 class, give it a slight watermarked green looking color. And if it's definitely a good spot to go looking for bone, let's color that darker green. And so what we see is these darker green patches indicating where we may want to spend our time. Now, I don't believe this area over here, honestly. To the model, this looks like a good spot to go looking for bones. This, if I'm not mistaken, is in either the Triassic or the Permian. Permian predates dinosaurs. Triassic had some dinosaurs. There were tetrapods that lived in the Permian as well, but very hard to find those bones, not very likely. And anyway, this is kind of predicting whether it's brushy basin or not. So I give it a score of 0 over here. The model did not do well there. But this is fairly believable. All along this anticline or syncline, it's actually doing a pretty good job. In fact, right here, it said, yeah, you might want to go look for bones in this area. And we know for a fact that right here in this building, many, many, many dinosaur bones have been found. And you may have seen them if you've gone to the Carnegie Museum or other museums in the United States. So anyway, this is just looking at the scoring time and comparing the maps. And they compare favorably, and we're doing it faster. And so, so anyway, this is the idea. The models comparing PyTorch and IR, there was some differences in terms of comparing between PyTorch and IR, but for the most part, right on target. So this kind of wraps up the OpenVINO chunk, but I'm going to go into another thing. I want to show you our latest and greatest map, and it's going to look quite a bit different from this one. This one was fairly crude and blocky, and we wanted to make it a better resolution map. Okay, so now on to heat map generation. This is the map that I'm really a little bit happier about. What we're able to do now, since we can score these things a little bit faster now than when I first started, we can score them quite a bit faster. And so before we had to do those blocky, square by square things, and we just didn't have enough time to do what I wanted to do. But imagine what we could do is we could take a square here and get a value for its class. We could scoot it over a few pixels and get a score for its class, and scoot it over a few pixels and get a new score. And then we move it down here and down here and down here. Well, what we could do is we could average how many times has this pixel been evaluated. Once, okay, not now, not now, not now. It did it one time, not now, not now. But this pixel right here was scored here, and I move it over here. It's scored there, scored there, scored there, scored here, 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 here. And so it's scored quite a bit of times for a given pixel. So what we can do is keep track of the number of accounts, the count frequency of each pixel. Has it been scored how many times, basically? And so we can then get those scores and average them according to those counts. And so we can get an average score for every single pixel on the screen, or every 8 pixels, or whatever. We can adjust the granularity. And when you do that, you get a map that looks more like this. So, when you take that same image patch and patch it to the model, it may say it's a 1 if you give it right here. But if you take that same image patch and just move it, just clip off 2 or 3 pixels off the edge and put 2 or 3 new pixels, columns, Y is on the right, and rescore that, it may say, that's a 0, right? And so you need to kind of get an average of all those predictions and see what the model says. And that's what we're doing here. And this is what the map looks like. And this is just, I'm not going to go through all the code to do this, but it's just to give you a sense of what we're doing. In this case, I'm using 6 epochs. I'm using IPEX is set to true. In this particular case, I'm not using the OpenVINO model. I intended to get back and run that one right here, but we had also sped up the IPEX model, and so I'm going to use that one right here. And so we'll set this to eval mode. We'll load up the latest, greatest model that I baked. Here's what that model looks like. And we define just some functions to do inferencing and so forth, showing the data denormalizing as before. And then we're going to load the data in. We're going to infer against it. And we see some 0s and some 1s and so forth. I don't see any 2s in this batch. But then what we're going to do is inference given that large batch of images. And so what we can do is take a larger image from Dinosaur National Monument that you've just seen, and I can subdivide it into smaller chunks. And we get an example of that image, and I'm just going to crop down and look at the area near where that Dinosaur National Monument excavation is. And then we can just evaluate and see what it does. In this case, it would come back as a score of 1. Well, then we can give it this entire map right here. And so here's the little building. And, this represents maybe 300 meters by 300 meters or something like that. So this is a fairly extensive place. In 100-degree heat, you don't want to be going and randomly searching all of this stuff. It's brutal. It's very brutal. It'd be deadly. So you'd like to concentrate your efforts, bring lots of water, concentrate your efforts, and see what the map says. And so we read this large image. In this case, it took 2 minutes to do. And we compute those sliding tiles. And then we just do the heat map. And this is the result of the heat map. Now, with 6, it's not showing the Dinosaur National Monument building right here with just those 6 epochs that we did. But it is showing some high areas of interest over here in red. Now, I changed the color scheme. Blue meaning cold, like, hide and seek. You're hot or you're cold. Blue is cold, red is hot. So we want to go to the red areas. If we play with this model enough, we do get this, again, predicting that this is a decent area right around the Dinosaur National Monument. But it also predicts areas that we've actually gone out in the ground and just watched. These aren't advertised as bones by anybody at Dinosaur National Monument. You're free to just walk around and look around. And these are bones that we found. So we found a landslid in situ bone here, and in situ in a cliff face over here somewhere, and then some floats, some dinosaur bones just laying on the ground. And so I was pretty pleased with this. I would have liked it to be a little more solid red there. It's pinker, but not bad. And this is for those 6 epochs or so. So when you keep playing with this, we actually were able to generate this map up here at the top, which was, I think, my best map so far. And so we were able to do this with this one. And then we were, okay, but people have known about Dinosaur National Monument for a century, of course, let's go look at Dinosaur National Monument. So maybe you're not so impressed that the model is doing what it's doing. But let me take you back to the slides, and let me show you the result of one of our dinosaur trips. I'm about to take you on an AI adventure, a journey of using AI to find dinosaur bones adventure. And so what we're seeing here is the result of a map that we made, not in Dinosaur National Monument. This is several hundred miles away in an aerial area near Moab, Utah. It is now being recognized as a really great bone location to go look for stuff. It's actually now part of something called Utah Raptor State Park. But a lot of this stuff was being done that when we were exploring, we didn't know about that. And so, but we found some bones, and we found them using AI. Here is one of our early AI maps with our tracks and dinosaur bone fragment finds. Join us as our drone touches down and Ben describes our AI bone find.
We found it.
Did you find some bone?
That is a nice bone.
Not bad. So it's a limb?
Yep.
Small limb.
Outer bone, kind of brown, red.
Oh, good job.
There.
Good
yeah,
job.
You can see the core is more spongy and then hard at the exterior. Yeah, that's the perfect cross section there. Awesome.
Way to go. AI bone. So that's why we get so excited, and that's why we're excited also about the AI, because it was about 100 degrees, 101 degrees when we were out there doing that. We could only spend about 2 hours out there, hot, sweaty, very hot. And we only walked a mile or two, and it was brutal. And so being able to concentrate our efforts in this green mapped area guided us into these bone finds that were all found effectively, but using our AI. And so what do I mean by that? It guided us to the green areas, and then we had to go put the tracks through the green areas and look for bone. So it wasn't an X marks spot kind of a map, but we did find bone as a result of being able to be targeted at where to look. So with that, we're approaching the end here. I just want to say that I'm looking at some other applications of this same kind of idea. One could be in the use of fire prediction. So we just had in 2022 the largest forest fire in New Mexico's history. It's 2 fires that combined, and 340 some odd thousand acres, lots of structures destroyed, families displaced, and so forth. A lot of wildlife killed, and cattle and so forth. So if you could look at areas and predict, and be of service maybe to the U.S. Forest Service to be able to say, well, if you want to do some thinning out areas or something, maybe these are some of the areas, or maybe for controlled burns. Controlled burns actually cause this fire, actually. So maybe that's not a good idea. Maybe it is. But this is one of the areas where, very similar to the bone hunting, I think we can, I'm working on it right now to see if we can use it to predict areas where there's a higher likelihood of the fires, given either road patterns where they can't get in and form fire breaks, or locations close to power lines, close to small villages or cities where there could be aged power line utilities and so forth. Or in the middle case, this is for energy and production regulatory compliance. This is another area in New Mexico showing old scarring and new scarring of areas where they're doing energy exploration. And so this is on state leased lands. And so the state is owed the revenue if people are out there doing that stuff and they have those leases. So that would be a way of doing regulatory compliance. And then just for planetary exploration for water or life, past life, hey, we're looking at, with our dinosaur thing, at sedimentary rocks and determining, where sediments were. And so, could we do the same thing on Mars or other planets to help expedite finding the most likely areas for them to target landers and so forth like that. So these are just some of the ways that we could apply the same idea, I think. Now, one of the things I want to leave you with is to please obey all the laws. It is illegal to remove vertebrate fossils from public lands. Private landowners have the right to remove any fossils like this that are on their land, and they can grant permission. So bones do wind up in rock shops and stuff like that. And reputable shops will have bones from private lands. You're not allowed to collect them from public lands, and we do not. And so I would just don't do it. It's going to be a big problem for you if you go collecting bones on public lands. So don't take them. Take pictures of them, take videos, build memories like I've done with my family, and report it to the museum, to a paleontologist or whatever, and let them do the ones that know exactly how to do the extractions. We have had the opportunity to go out on extractions for some of the bones that we found because we reported it to the museum, and they said, hey, that looks like an important fossil. And so we were able to go out with them and extract a few. But leave it to the hands of those guys and don't take them yourselves, not even the little fragments, because that messes up the clustering. You won't know. You don't know that dinosaur bones are there. That small little fragment pile might be telling you something about a really important find just right next door. So please leave them there. And with that, we're pretty much wrapped up for the series. Thank you. Really enjoyed this time with you guys.